Welcome to this week's lab discussion, week 5, discovering the modification of stream-eroded landscapes by glaciation. As we do each week, we will start with a review of the last lab and then go into an introduction of the methods and principles being used in this laboratory. Last lab, we were talking about stream-eroded landscapes, and we were working with topographic maps and profiles as a way of studying the landscape in a particular area. This area has been eroded over time by the relentless work of water running downhill. And we're applying what we've learned in lectures and readings to this particular example, where we're looking at the Mancos River and tributaries to the Mancos River. So I'm not going to go over every question in the laboratory. I'm going to really focus on where those questions are going. Those questions are going to look at how this system evolves over time. And we start here. This is a portion of the map of the Mancos River area. And you can see Johnson Canyon flowing into that. Johnson Canyon is a tributary of the Mancos River in as much as it contributes water and sediment to the Mancos River itself. Extending to the north and south of the east-west directed Johnson Canyon are a number of smaller tributaries feeding into that. And in this laboratory, whenever it was referring to just simply tributary, it meant a tributary to the Johnson Canyon. And Johnson Canyon is a tributary to the Mancos River. Flowing through Johnson Canyon is an intermittent stream. That means when it rains, the water is flowing. It's also flowing through the other tributaries. When it's dry, there's no water flowing through the bottom of Johnson Canyon. Mancos River is a permanent stream, so water is virtually always running through the Mancos River. You'll see on this particular map the location of cross-sections you were actually asked to look at by forming topographic profiles. So let's look at that first. So here's a topographic profile across Johnson Canyon. You're asked to construct this as well as construct one for the Mancos River Canyon. And to do this, I've already put on the line the data points. The data points represent elevations where contour lines cross the line of profile. These are really important. If you were doing this on your own, you would mark those important points along the line of profile. This is the line of profile B to B prime. Now, one mistake students make when putting a profile together is they don't always line up the data transfer to the vertical profile. And in part, that's because some of the examples you were given, it's lined up for you. But if you remember my example from the laboratory discussion and the example used for topographic profiles in the video you were asked to watch in Module 1, you'll note that the technique when you don't have things automatically lined up between the vertical section and your line of profile on the map is to take the edge of a sheet of paper and line it up. So we're going to kind of do that here. This is how you should transfer the data. The data can't be transferred straight down. When you do that, you are completely distorting the elevation data, and what you come out with is absolutely useless. I can't tell you how many times while reviewing laboratories I'm getting that from students because they're just drawing lines straight down from one to the other. When we properly transfer the data down, and we've gone through constructing profiles now several times, the profile you get for Johnson Canyon looks like this. It's a V-shaped canyon, typical of streams that are cutting down through the landscape that haven't evolved very far. This is a closer look at that profile. By contrast, the Mancos River Canyon is much wider and has a developed floodplain at the bottom. This is typical of streams that have been evolving for a longer period of time. Over time, we see some trends. Those trends are through channel downcutting and headward erosion, streams get longer. Another trend we see is the canyons that they're flowing through get wider because as the slope gradient drops, the development of meanders forces streams to start carving out the canyon at the base. And then during flood stage, flooding will put flat deposits on top of that canyon that's being carved out. So those are the two. This is A to A prime across the Mancos River Canyon. You compare it to the Johnson Canyon's more V-shaped profile, and we get a sense of how things are changing and evolving in this particular landscape. Now, another type of profile you're asked to do is not a topographic profile at all. Rather, it is a long profile. Long profile or longitudinal profile is a plot of distance versus elevation drop over the length of a stream. And here you can see the data laid out for you. And what's really important are for each station the elevation and the cumulative distance. So the cumulative distance is here, and the cumulative distance just comes from the measurement from one station to the next added up from station A. Here's the elevation. So these are the two things that you're going to be plotting. The cumulative distance is along the horizontal axis. The elevation is along the vertical axis, and that kind of makes sense. The other thing is you were given a particular horizontal scale to use, and that's kind of important. The horizontal scale that was chosen for you is 2 centimeters equals a mile. That means every 2 millimeters equals 1/10 of a mile. And that gives you an easy plotting for this. And this is the plot, roughly speaking. There's a little bump in the data between D and E, but for the most part what you see is a steeper profile up near the headwaters, becoming more gentle as you get towards F. F is at the confluence between the adjoining stream to the Mancos River. Now, when we look at that, that kind of makes sense because through channel downcutting and stream headward erosion, we tend to get a very much preserved long profile that's steep in the back, and in any particular location, the slope gradient is becoming more gentle. So one of the things you're asked to do is to take all these observations and looking at the profiles you constructed and come up with answers to Table 2. And I'm showing you them here, and these are just straightforward observations. The Mancos River, compared to Johnson Canyon, which is a tributary to the Mancos River, and compared to a tributary of the Johnson Canyon, the sizes are very easily observed as the Mancos River is the biggest. Johnson Canyon is intermediate, and the tributary is smaller. In terms of width, Mancos River is wide. Johnson Canyon is intermediate, and the tributary is narrow. As far as the slope gradient, the Mancos River has a relatively gentle slope gradient. The Johnson Canyon slope gradient is intermediate, and then the tributary slope gradient is steep. Now remember, slope gradient isn't about the steepness of the sides of the canyon, but changes in elevation along the length of the stream. Slope gradient is seen visually when we look at a long profile. Then finally, you have age, and age is not an observation here, it's a conclusion. It's a conclusion based on your observations. The Mancos River is old. Johnson Canyon is middle in age, and the tributary is young. And this is an important sort of conclusion based on your observations. And if you understand the relationship between things we've discussed in terms of evolution of streams and things like headward erosion is going to make your stream longer, the canyon is going to become wider over time. So those streams that are longer and wider, bigger, and have a more gentle slope gradient because the slope gradient is being worn down over time are going to be older. And so that's where you're going to get your age relationships from. But it's even bigger. If I were here and if my late father were alive and still here, and perhaps my oldest son were with me, there'd be 3 generations of DiLeonardos. And you would say my father is oldest because he'd been around longer. And then I would be the one in the middle, the middle-aged one, because I'm in between my father and my son's age. What does that mean? It means I haven't been around on the planet as long as my father, but I've been around longer than my son, and so on. The same thing holds up for stream systems. Barring the nasty business of stream piracy, which we're not going to get into, in an evolving stream system, tributaries are always younger than the streams they flow into. And the reason is this: as a stream evolves headward from the margin of a continent, let's say inland, it gets longer. But as it digs a stream, it also gives you an elevation change between the edge of the stream and the bottom of the canyon. New streams flow down into the canyon, forming completely new canyons on their own. These are the tributaries, and in turn, they do the same. The implication when we talk about generations of DiLeonardos is I couldn't be here if my father wasn't here, and my son couldn't be here if I wasn't and his grandfather wasn't here. The same is true in an integrated stream system. The younger streams are only there because the older streams were there first. That's what providing what we refer to in lecture as the H, the elevation change that gives you the energy to cause that erosion. So this gives you an understanding of modification of stream systems. And these stream systems are prevalent all over the world in most tropical and temperate climates. It's most of the surface of the earth. We see some modification to that in desert environments. We also see modifications of that in glacial environments. So the laboratory we're doing this week is discovering the modification of stream-eroded landscapes by glaciation. And this is something we're going to see prevalent in western North America, which didn't have a large glacier existing over it. Instead, it had alpine glaciers that grew during the last 4 ice ages in the northern hemisphere. And in each of those cases, in the alpine environment, stream-eroded landscapes were modified by glaciation. And then, once the climate warmed up, what we saw was the retreat of the glaciers and the capture of that landscape by stream flow again, but it leaves behind the remnant of modified landscapes from glaciation. And that's what we're going to be doing, is looking at landscapes in alpine environments. And we're going to look at a particular landscape. Probably the best place to do this is in the Yosemite Valley. In the Yosemite Valley, at the end of the Yosemite Valley, you have something called the Merced Gorge. The Merced River flows through Yosemite Valley, makes a turn to the south, flows out of the Sierras, coming down to the south and then back out to the west. And we see a huge change in the landscape. And that change coincides with where the furthest extent of glaciation occurred in the Yosemite Valley during the last ice age, and where it was always eroded by the Merced River. This makes it an ideal location to study modification of stream-eroded landscapes. Why? Because we're looking at the same stream system. We're looking at the same landscape. Upstream, along the Merced River, what you would expect to see are examples of more youthful stream features, but instead we see something else. And that something else gives us a real clue that we're being modified by glaciation. This is also going to give us an insight and a reinforcement of our understanding of how glaciers modify the stream system. Remember in lecture we talked about streams modifying the landscape as if they're the world's largest chainsaw cutting down into the landscape. It's the speed and the grit that's cutting into the landscape. We're going to see that's not true for glaciers at all. And we're going to do it first by drawing some topographic profiles. These are things that we're pretty used to. And one that you're going to do is A to A prime. And you can see again, I've taken the data for you. So made it easier. And remember, use the edge of a sheet of paper to transfer the data. Do not just draw it straight down onto the piece of paper. It has to line up from A to A prime so that the elevations match their actual horizontal locations. This is the horizontal map. The horizontal distance is whatever the map scale is. I put in the vertical elevations for you, so it's simply plotting the elevations. Remember, the profile isn't complete until you draw a smooth line going from A to A prime, that is from one side to the other, and it is constrained by the elevation points. The elevation points are not the profile, they're simply the guide rails, if you will, for the profile. Put together a reasonable construction, and remember all the rules of topographic maps and topographic profile constructions. You're going to do the same now across the Yosemite Valley, and this is from B to B prime. And yes, it's going to take you a few minutes to do this. The lab normally takes several hours to do. And this particular lab is no different. You're going to have to put together a topographic profile across the Yosemite Valley, and you're going to see they're strikingly different. Here's a topographic profile across Bridal Veil Falls. It's highlighted in the labs, and you can see it has a particular shape. Bridal Veil Falls is the location of a glacial tributary into the main glacier that was flowing through Yosemite Valley when Yosemite Valley was subject to glacial erosion during the last ice age. Now, I've given you a couple of digital maps. These digital maps are for one of the other things you're doing in this exercise. The two real focuses here to look at how glaciers are eroding into the landscape compared to stream erosion is to compare the shape of the canyon, and that you're doing through topographic profiles, and then changes in slope gradient. So the first that you're going to deal with in terms of slope gradient is here. This is the digital map I put together for the Merced River through the Merced Gorge. And remember that slope gradient is equal to rise over run. When we say slope equals rise over run, they don't really mean that in mathematics. They really mean the change in y over the change in x. But for us, we really do mean rise, the change in elevation, over run, the change in distance. And you can see I have locations here from y to x showing each data point along the way of where a measurement was made for distance and a change in the elevation. So the change in the elevation is the difference between 2,200 feet and 3,600 feet. So when you get the slope gradient, you're going to take the elevation change by taking 3,600 feet and subtracting 2,200 feet. Most math you need in the course, right? A little addition and division. And then the change in distance. The change in distance is shown here on the map. In this particular case, we start at 0 at y and end up at 5.64 miles. Just go back to that for a moment. 5.64 miles. So what you're going to do is take that elevation change and divide it by 5.64 miles, which is the change in distance. You're going to do the same thing here for the Merced River flowing through the Yosemite Valley, and you can see that I've blown up the start of this location at X, which has an elevation, I believe it's 3,800 feet, maybe 3,860. And then you have y at 4,000 feet. So you want to take a look at the elevation at x, the elevation at y. That's the change in elevation. And then the change in distance is going to be shown here. And you're going to do exactly what you did for the Merced Gorge. You're going to be looking at rise over run, right? You're going to look at the change in elevation. You do that by subtracting the elevation at y and the elevation x. So you have y and subtract from that the x elevation, and then take the total distance, which you can find next to y, which is a sum of all those measurement points you can see on the digital map. That will give you the slope gradient. Compare the two, and you're going to see a huge difference. Understanding the different way that glaciers modified the landscape as opposed to stream erosion is a real base for understanding the landscape evolution in alpine areas, especially in Western North America, but you find these all over the world where we've had modification of stream eroded landscapes by glaciation. So I will meet back with you next week and discuss the ramifications of this particular laboratory. And I know you're all preparing for the midterm exam as well, and I'd like to wish you good luck with that.